Let's see what it's asking us. Okay, so basically the idea is that we're given a chessboard, we've got a knight, and we're given the position of the knight on the chessboard. And what we want to be able to tell is how many different moves can this knight make? We'll say it's their turn to move. How many different spots would they be able to reach from where they are right now? And we're given their original position, we're given the cell that they're starting on, but we're given the cell in kind of in a very chessy way, right? So it's like A1 or C2, you know, it's in what they call algebraic notation. So chess notation, you know, just according to the legend on the board over here. Okay, so basically that's the idea. For anyone who's not really familiar with the game of chess, a knight moves in, sort of like an L shape, so they can either go like, let me grab an appropriate color. Yeah, sort of a lime green would be nice, I think. So like 2 this way, 1 this way. That's a knight move. 2 up, 1 to the right. 2 down, 1 to the left, you know, that sort of thing. So any L shape you can imagine, they can do it. And we want to know how many different moves there are. So keep in mind, like, what we're really talking about is the number of different spots they'd be able to reach. So like, for example, going 2 down and 1 to the left is the same as going 1 to the left and then 2 down. It's a matter of where they end up, which spot they end up at the end of that. Okay, so that's our goal. That's what we want to be able to do. We want to figure out how many spaces there are going to be that this knight can move to. So I was thinking about it, and it's been kind of a little while since we've really done kind of a wacky solution. I guess in the mood to do something a little bit devious, so let's actually create the board. I think that would be a nice way to do this one. We'll create a chessboard, we'll put the knight on the chessboard, we'll think about how they can move around from there. But basically, let's make a list. This is another thing we haven't done in a while. So we'll say, create the chessboard, okay, place the knight, and that'll probably involve finding its coordinates, so /find coordinates. What do we want to do after that? I guess find the squares the knight could move to. Yeah, that's basically what we want to do, right? So, okay, we'll start by creating the chessboard. Then we'll place the knight after that. But for now, creating the chessboard, let's just say let board be assigned the value of this empty array. And I mean, ultimately this array is going to be a matrix. So we're going to say for let I be assigned the value 0, I is less than 8, I plus plus. Why 8? Well, it's 8 squares wide and also 8 squares tall or long. It's 8 by 8. That's the main thing. Okay, so then within this outer loop, we're going to say let row be assigned the value of empty array. And at the end of this, we're going to say board.push row. But before we do that, we have to fill up the row. So we'll say for let j be assigned the value of 0, j is less than 8, and j plus plus. And within this, we're going to do row.push something. What are we going to put in here? I'll call it tile, because that's really what we're looking at. And what is tile? It's going to be, here, let's just go with a hashtag for now. Okay. And then at this point, let's just return the board. We'll see what we're looking at here. Okay, great. So is this 8 by 8? Yeah, it looks like it's 8 by 8, so that's good. But it doesn't really have that sort of chessboard feel. So maybe we could do something like tile is, I don't know, j mod 2. J mod 2. And basically if j mod 2 gives us, okay, j is our iterator here. It's going from 0 to 8. We're dividing it by 2 and looking for the remainder. That's what our modulus is doing here. It's just giving the remainder. So either it's going to give a 1 or a 0. If it's going to give a 1, that's considered true, so it'll give us that hashtag there. And actually, maybe that's what we want for the false one. No, actually, that's good. Yeah, that'll be the true one. Then for the false one, we'll put a space. There we go. Sorry about the hesitation on that one. Let's run this and see what kind of a difference it makes. And by the way, we're using a ternary operator here, right? So remember, this is the same as saying if j mod 2, then this, else this. Okay, so same sort of thing here. It's just a lot more efficient this way. But we have a bit of a problem, and it's that it's still not looking checkerboardy. It's looking kind of stripy instead. That's because I'm only looking at j in here. So in order to make it actually depend on I as well, I'm not just going to make it j mod 2. I'm going to make it I plus j mod 2. And the reason is because if we're looking at this, or I guess we'd be down here actually, yeah. So here we would say like I is 0 and j is 0. Over here, I is still 0, j would be 1. Whereas over here, I is 1 and j is 0. So if we add the 2 and then take our modulus, we should find that now it's going to depend not just on the row, but on the column as well. And nice. Okay, so this is good. So this is looking a lot like a chessboard. That's awesome. Nice stuff. So right off the bat, we've got our chessboard. I think we're done with this first section over here, so that's nice. And then maybe we won't return the board anymore, just so that it'll keep going to the next thing, which is to place the knight and find its coordinates. So how are we going to find the coordinates? Well, let's take a look at what our cell is looking like, our input here. So it's something like a C2. How do we want that to translate? So C2 would kind of be like, the third row, the second column. So basically we want to do two things. We want to take the first character and we basically want to compare it to the character code of lowercase a. We want to say how far away is this from the character A. If it is A, then we expect 0, that'd be row 0. If it's B, that would be row 1. If it's C, that would be row 2. So we're looking for the difference between the character code of this thing and the character code of lowercase a. So let's start with that. We'll say, actually, not even a let, we're going to say const, because we're not actually going to change the starting position of the knight. We'll change the current position of the knight, like it'll move to other places, but for the starting position, that's not going to change, so we're going to keep that a constant. Okay, so what's it going to be? Well, first of all, it's going to be cell.character code at 0. We want to know the character code, or like the ASCII code, if we're looking at this table again, of the first character, or of the 0th character, technically. So if it's C2, it's going to say, okay, what's the ASCII code of this character? It's a C, so that would be a 99. And we want to subtract from that the character code of A, which is 97, so that would give us 2, and row 2 is what we want, or the row with index 2 is what we want. So I'll just do this, a character code at. Okay. And I know, I could just use 97 for this. I could just make this a constant or something like that. But we're not going to be using this more than once, so I'm just going to keep it like that for now. Okay, so that's going to be x. And now for y, we could say, well, it's already right here, We've just got this 2 that we want to use. But a couple issues with that. So, we might be tempted to just say this, right? Cell at 1, or even cell.character at 1. It would give us the same thing. But there are two reasons we don't want to do it this way. Number one, we're not looking for a string. We're looking for an integer. So we're going to want to do a parse int on that thing. And we could also just multiply it by 1 or something like that. But I'm trying to be proper here. So, okay, that'll turn it into an integer. Then the other thing is, well, 2 is actually a bit misleading, because if you take a look at this, it goes 1, 2, 3. It doesn't start at 0. We want it to start at 0. We have a 0-based matrix here that we're working with. So actually, I'm going to just shave off a 1 from that, because, our x coordinate does start at 0. Okay, so now we've got the coordinates of our knight, and now we want to place our knight somewhere. So let's say board at x at y is assigned the value of, and I guess we need some way of representing our knight here. We could just use the letter K, which I guess should be in a string, so quotation marks there, and then just for now we'll just return the board, see what it's looking like. Okay, so there's the knight, right, where the character K is. And good, yeah, that's where we expect it to be. Now, if we wanted to make this a little more interesting, instead of just the K character, we could do something like, check this out, String.fromCharCode. So this is the sort of thing where, like, you know, I can just take a character code. If I wanted K here, I would just take 75. I would say from character code 75. And this should really look no different. It's still just going to have a K in there. But I'm going to go way off the table here, and I'm going to do some other ASCII code. I mean, even here we have extended ASCII codes, but it only goes up to 255. There are other codes. There are other characters. So I'm going to go with actually a huge one here, 9,822. Why this one? Well, I somehow think this is going to be appropriate to this question. Check it out. We got a little chessKnight in there. Okay, so the only problem with this is it doesn't actually respect the monospace font here, so it is a bit wider than the other characters, which means it kind of shifts this over. So, is it worth it? You know, should we make that sacrifice? Yeah, I'd say it's probably worth it. Okay, cool. So the thing is, okay, we want to find the squares that the knight can move to. We've got our initial position for the knight, but we want to know where can the knight move to from here. So what we're going to do is, let's say, okay, we're going to do, let temporary x be assigned the value of x plus, let's say 2. And we'll say let temporary y be y plus, we'll say 1. Okay, something like that. All right, so then we've got a temp x, temp y, and then all we need to do, because basically what we're trying to say is, you know, if we move 2 this way, 1 that way, are we still going to be on the board? So all we need to do for that is to just say, well, okay, there are a few ways we could do that. We could do something like if, you know, 0 is less than or equal to temporary x, and temporary x is less than or equal to 8, and et cetera, right? Like we need to check temporary y as well. But because we actually created the board, because we actually have a matrix here, we don't have to do it that way. We could just say temp x in board, and temp y in board at 0. Why board at 0? Well, technically it wouldn't make much of a difference here because they're the same dimensions, right? They're both 8. They both have a length of 8. You go from 0 to 8. But, you know, just in case this wasn't a square board, in case instead of being 8 by 8, what if it was like 10 by 19 or something like that? Then basically I would want temp x to be like the number of rows, I want it to be within the number of rows, and I would want temp y to be within the number of columns. So the idea is that board at 0 is an array. It's like a row of squares here. So it also goes from 0 to 8. So it doesn't make much of a difference here, but you know, probably just worth it to be proper like that. So okay, that's nice that we don't have a bunch of like double inequalities and stuff like that. So we'll say if those are, you know, on board, then for now we'll just say board at temp x and temp y is assigned the value of, I'll just use the character x to represent, I guess, like a threatened tile, a possibility that the knight can move to. So let's run that, and we'll see if that works. Okay, so there we go. We've got the x over there. What about our next one over here? Yeah. We got the x over there. How about the one down here? There's the x, and the one after that. We don't see it because it's off the board in this case. Okay, and that's fine. That's fine. That actually tells us that this is working the way we want it to, because otherwise, if this wasn't here, it would have an error. It would freak out about this. It would be like, oh, can't find index 6 of undefined or something like that, right? So actually maybe we should try that. Let's just let's get this out of here. Let's just put it here and let's see if that actually does give us an error. Exactly. Okay, so can't set property 6 of undefined. What'd I tell you? All right, great. So there we go. We'll put that back in there and everything's working the way we want it to. Well, sort of the way we want it to. I mean, the problem is we're only really looking at one possibility here. Like, couldn't the knight move to this spot, or like, you know, this spot over here, or like, you know, up there or over here? Like there should be a lot more spots that the knight can move to. So we should probably try to find all of those. There are a few ways we could do this, but if we want to list all the possibilities, it gets kind of complicated, right? Because it could be that actually here, let me do it this way. You know, I could say like let dx be assigned the value of 2, let dy be assigned the value of 1, and then we'll do plus dx over here and plus dy. So the d just for like delta, change in x, change in y. And now if we think about this, well, basically, okay, dx, it could be 2 and dy could be 1. Or we could flip those where dx is 1, dy is 2. But then what about negatives? So then we also have like, you know, where dx is negative 2, where dy is negative 1, or where dx is negative 1 and dy is negative 2. But then what about mixing them? What if dx is positive 2 and dy is negative 1? It gets complicated. There are a lot of situations to keep in mind here. So what I'm going to do for this is a bit different. So I'm going to do loops. I'm going to do 2 nested loops. I'm going to say for let dx be assigned the value of negative 2, dx is less than or equal to 2 dx plus plus. So basically it's going all the way from negative 2 to negative 1, and dy is going to do the same. It's going to go from negative 2 to positive 2, and there we go. Yeah, negative 2 to positive 2. Is that what I said before? I might not have. Anyway, my apologies if I didn't. Point is, both of these are going from negative 2 to positive 2 in the inclusive range. So they do include both negative 2 and positive 2. Okay, now if we do it this way, if we give this a run, this might not be exactly what we're looking for either. And it certainly isn't. Partly because it's covering way more squares than we want it to. Like, look at that huge block of squares. And also, it's overwriting that cool knight character that we had in there before, which is just no good. So we need to put some boundaries on this. We need to say something like if something, and, well, okay. You know, if dx is equal to 2 and dy is equal to 1. There we go. Is that better? I'm having weird indenting happening here, so let's see. That's better. All right, and let's take this and put it up here, because we don't want that to fire if we don't have the right kind of dx and dy over here. Okay, so this is kind of what I was saying before. We could try to list all the possibilities, like if dx is 2 and dy is 1, or if dx is 1 and dy is 2. And we could make this really, really long. It could go on and on and on and on, going through all the possibilities. Like, basically, it's 8 unique situations that we would need to cover. We would need to, and each of those situations has a dx and a dy component, so it'd be like if dx is this and dy is this, or if dx is this and dy is this, or we'd have like 16 booleans all strung together there. That would be a real pain. So instead, there's something I want to point out. When we're moving in an L shape, how many squares are we moving in total? Well, it's 3. We're saying 1, 2, 3. 1, 2, 3. Moving 3 squares. Now, the only other way we could move 3 squares without doing an L shape is if we're going in one direction the whole time, like 1, 2, 3. The thing is, we're never going to have that situation if dx and dy are only going from negative 2 to positive 2. They never reach 3. So basically, if we've moved a total of 3 squares, it must be one of these 8. And just to sort of clarify what I mean by that, and I'll try to get an appropriate color, it couldn't be this one, this one, this one, or this one. And these over here are the only 12 squares that are exactly 3 moves away from where the knight is right now. Okay, so that's basically the idea. We need to check, well, is the total number of moves equal to 3? Great. But how do we find the total number of moves? Well, it's basically dx plus dy, but there's just one issue. dx and dy can both be negative or positive, so we specifically want to look at like the absolute value. How many squares did we move? Math.abs dx plus math.abs dy equals 3. If we're moving exactly 3 squares. And let's see if that's going to work. So, okay, these look good. They look like the right ones, but that's right in the corner. So let's find one that's not. And notice we're not getting overwritten here, so that's good. Look at that. These seem to be exactly the moves we're looking for. Is this the example they give us here? D4? No, this one's D5, but it's pretty similar. Okay. All right, so that's looking good. It's looking awesome, actually. But the thing is, we're not passing any tests because we're not returning the thing that we're supposed to. So instead of returning the board, let's do a console log on that. So we'll say console.log board, just so we can see it, just for fun, really. And what we actually want to return here is moves. How many moves does this knight have? And let's get that started, I guess right here. So we'll say, let moves be 0. And actually, maybe I should move that down because it'd be more appropriate to have that under the comment that says find the squares the knight could move to. Okay, great. So moves starts as 0. We're going to return moves at the end, but when should we increment it? Well, it's basically as soon as we find a place that the knight can move to. So anytime that we're marking one of these X's, let's say moves plus plus. Okay, cool. And now let's try running that. Ooh. Nice. Okay, good. So that's passing all of our visible tests. And not only is it passing them, but it's giving us this cool little console log here that shows us where the knight is on the chessboard. It shows us all the spots that the knight can move to. And actually, you know what? I'm going to change this to capital O. And that's just to sort of emulate what they have over here, just to make it look a bit more like, yeah, cool. That's more like the picture over here. Well, that's awesome. Okay, so nice to have a visual to go along with that. That's pretty cool. And let's go ahead and submit that now. Ah, what a feeling. Okay, awesome. So let's close that for now. Oh, hey, that's really nice of you to say. Thanks, but not right now. Oh, wow, look at this. We're just getting showered with good news today. That feels good. We're finally a trainee level 2, 2 stars, 2 swords. Nice little wood grain on there too. That's a well-designed little badge there, Someone did some nice work on that. I like that sort of flat design of it. Very cool. All right, let's close that for now. All right, so basically returning to what we have here, in some ways, this algorithm is, it's really nice. It's doing this kind of stuff. Like, this is probably my favorite part here, the equals 3 thing that basically just gave us the proper squares. But it's kind of overkill in some ways too. In particular, I don't actually think we need to make the board. I think it's fun and whimsical, and I think it's neat that we do, and that we get, where do things go? Let's get those console logs back in the mix. Yeah. I think that's kind of cool to have this visual here. They say a picture's worth 1,000 words, but really, we don't need 1,000 words. We just need a single number. We want to know what is the number, how many moves are there going to be. So let's retool this. We're going to archive this one. We're going to wrap it up and in a nice big comment, and then let's get the inside here, and we're going to modify it. So we'll do some surgery on this. Okay, so first of all, instead of creating the chessboard, let's just not do that. Okay, great. So, and instead of placing the knight, we're just going to find the, I guess I should be specific, find the knight coordinates. Okay, cool. And we're going to not do that. Great. And then we want to find the squares the knight could move to. Okay, so this part's going to stay more or less the same. We're going to have moves. It's going to start as 0. We're not going to console log board because it's gone. We're not going to have this part because there's no more board. And that means we actually can't have this part either since there's no more board. So that's the one thing I'm a bit remorseful about for this one. Let me just get a bit more room so we can see all this at once. Okay, cool. I do really like the fact that we're able to do this, but is it worth the extra memory of having that whole board matrix declared and all that? I don't think so. So what we're going to do instead is basically what we were looking at before. Temp(x) is less than 0, and temp(x), it's greater than 0, greater than or equal to 0, and it's less than or equal to 8. Or I guess technically, actually, it has to be strictly less than 8. It could be equal to 0, but it does have to be less than 8. Strictly less than. Yeah, because, it couldn't, we wouldn't be able to actually have it be 8, because then that would be, like, off the board. The length is 8. It's got to be length minus 1. Okay, so that has to be true. And what else has to be true? Well, basically same thing, but for temp y. So, yeah, that and temp y is less than 8. And is that going to work? Well, let's try it. I don't think there's anything here that's going to cause a problem. So, yeah, great. It's passing the test. I guess we can make that bigger now. So that's probably a little nicer. We don't have to worry about having a whole matrix in memory or anything like that. If the length of this thing over here is bothering you, we could separate it. You know, we could do something like that, if that feels better. Yeah, I like that a little better. We're seeing temp x on one line, temp y on the other line, and we got our two double inequalities here. And I'd say this looks pretty good overall. Turning moves. I don't think we're doing anything superfluous. I don't think we're being inefficient, wasting our time or anything like that. So yeah, I'm happy with this one, I think. I mean, I guess the real test is going to be this. We'll see if it passes the hidden test, and yeah, it does. Okay, so that's pretty cool. I like that one a little better. But, you know, I'm thinking we can do better than that still, because I'm looking at this and I'm seeing these nested loops, and I'm thinking, well, yeah, I know there are really only 8 squares we're looking at, but we are running this if statement. Like, we do at least need to check this for like quite a few possibilities here. I think like for about 25 possibilities. That's a lot more than 8. Still not that significant, but anyway, the point is, I'm just thinking if there's a way we could do it without these nested loops, maybe that would be a little nicer. I don't know. So let's archive this one as well. We'll put the comment blanket around it, and we'll grab this. We'll work from there. And here's the thing. I was thinking about this, and I was thinking, well, this problem's kind of interesting, I guess, but maybe it'd be more interesting if we could actually change like the dimensions of the board. If the board wasn't just like an 8x8 square, like if it was a big old rectangle, or like a thin strip or something like that. Like if one of the inputs, or if two of the inputs really in the question were like the dimensions of the board. And then maybe from there we can make it more interesting by saying, like, instead of just the starting square, maybe we're looking for like all the possible moves that the knight could take, like whether it's the sum of all of them or something like that. But then I started thinking about it and I realized, well, I think that's just mathematical. Like, if we had the coordinates, or sorry, the dimensions of the board, if we had like a length and width value, and we wanted to know the total number of knight moves possible on that board, I'm pretty sure we'd just be able to throw it into a quick formula and have it just like a big O of 1 sort of thing. So then I realized, yeah, I guess that wouldn't be that interesting. But having thought about that, it kind of inspired me to look at this in a different way. And so I kind of thought about it, and I thought, well, the reason it would just be a formula, the reason it would be sort of constant time, is because we kind of get this pattern emerging for how many moves there are going to be. And I want to show what that pattern is going to look like. So here's what we're going to do. We're going to bring back board. I'm going to say let board be assigned the value of this empty array here. And we're just going to do for let I be assigned the value of 0, I is less than 8, I plus plus. So the same sort of thing that we had before. For let j be assigned the value of 0, j is less than 8, j plus plus. And then what do we want to do inside each of these? Well, the same sort of thing as before. Let row be assigned the value of this empty row. We want to push the row onto the board, and I guess we want to return the board. But then, well, actually, okay, there's a bit of a difference in terms of what I want to do here. So I'm not just going to do like row.push of like a hashtag or something like that. I'm going to actually push in a number of moves that it's going to take to get to, or sorry, how many moves are possible from that spot on the board. That's what I mean. Okay, so what's our spot on the board? Well, basically, let's take this, and we'll take everything but the return moves part of that, and let's just put it all right in here. So where does this start? It starts right around there. Boom. Okay, so instead of this, we're just going to say let x be assigned the value of I, let y be assigned the value of j. And I don't know if I can make those constants anymore. I think I would have to make those lets, because they actually are going to be different for different iterations of the loop now. And then moves, yeah, we're just going to push that onto the row, push that onto the board, and we don't need the rest of this stuff. So this probably seems a lot more complicated right now, but it will get easier. Okay, so there we go. Look at this. What are we even looking at? Good question. This is basically, imagine your chessboard, this thing over here. What this is telling us is if your knight is standing right here, they got 6 possible moves. If they're standing right here, they got 8 moves. If they're right here, 3 moves. If they're unfortunate enough to be in the corner, 2 moves. Okay, so the point is, we now have this thing. And you might argue, like, well, it took a lot longer to generate that thing, you know? Like, now you've got all these nested loops and stuff like that. Is that really worth it? And no, it wouldn't be. So that's why I'm just going to do this. I'm going to say let board just be this thing. Okay, so I'm hard coding that in because we know that we're not looking for just any old chessboard. We're looking for we're looking at this particular one, this 8x8 chessboard. And now I can do this. I can find the knight coordinates. Great. And all I really need to do is return board at x at y. Let's see if that runs. Wow. Okay, so let's submit that. The thing is, this is going to run in constant time now. It doesn't depend on anything. Like, it doesn't matter which position we're looking at. Well, okay, I guess you could argue this was constant time as well. I mean, it had nested loops, but that doesn't mean that it's going to scale up according to our inputs. So that's worth considering, I guess. So, all right, they're both constant time, but this one doesn't have any loops in it. It's basically just we hard code in this board, and then we find one value from it. That's it. So I think in some ways that's a little simpler. There are ways that we could do this without like using a matrix. We could make just like one long array, and then instead of saying like board at x at y, we could do like board at 8 times x plus y or something like that, like make it the sort of thing where anyway, we would just sort of like flatten the matrix. I don't think there's much point in doing that. It's not like a huge thing anyway. It's not going to change size. It's always going to be like this. So yeah, I think ultimately these are all constant time algorithms. I don't think the length of the algorithm is going to depend on the location of our knight, like the cell here. So they're all constant time, but yeah, this one's nice and compact. Is it the best one? Well, I don't think I'd say it's the best one. It's not all that educational, I think probably this middle one is what I would use if it came down to it. If this was like a code battle or something like that, if the pressure was on. Yeah, this is probably the one I would go for. I do have a soft spot for the first one we used that actually created the board. I thought that was cool, especially with the actual chessKnight character in there. But anyway, it's up to you. Whichever one you like the best, do that one. That's what I'd say. Okay, cool. So we're done with this, I think. Yeah, we submitted this. Yeah, cool. Nice. All right, so then I guess we can move on from here. Nice job, everyone. We'll move out back to the Rainbow of Clarity. And